All right, y'all ready? We have to put the past behind us and move on. And we move into chapter 3. And is that the title of the chapter? Inverse functions? Yeah, it is. Okay. All right, so the first two sections of this chapter I'm not going to go through. All right, like in other words, I'm not assigning homework out of it. I'm not going to lecture over it. And the reason is because it is exponential functions, which was covered in college algebra. And then the next section after that, 3.2, is inverse functions and logarithms, which were also covered in college algebra. But these two sections are in this book as a reminder of the things that we learned in college algebra. I will point things out though, okay? So there are some important things that you need to remember from college algebra, specifically this whole idea of an exponential function. Exponential functions are any function where you have a raised to the x, where a is a number, and that number is bigger than 0 and not equal to 1. So 2 to the x, that's an exponential function. 5 to the x is an exponential function. And this is what they look like. We have avoided these functions, haven't we? We have avoided them. Yeah. This chapter, what we're going to do is we're going to incorporate these into our derivatives. Like we can take derivatives of a lot of things right now, but we have not taken derivative of an exponential function yet. We have also avoided logarithms. Now we will deal with them. Before we do that, we have to remember what they look like. So an exponential function will grow very rapidly, right? As you go out to infinity, the function goes up to infinity. As you go out to negative infinity, the function goes to 0. And that's what will happen if the base, is what we call that, is bigger than 1. Does anyone remember what happens if the base down here is like 1/2? It's the opposite. It looks like this. Instead of being what we call exponential growth in college algebra, this is referred to as exponential decay. So if the base number is between 0 and 1, you do this. If it's bigger than 1, it does that. I hope that rings a bell. There were properties of exponents from college algebra and even before college algebra that we will use. Things like if you have a base to a power times the same base to a power, you add the powers, right? If you have something to a power over the same thing to a power, you subtract the powers. We've done this already, right? Something to a power, raise the whole thing to a power, you multiply the powers. And then this last one, if you have a product to a power, you can apply the power to each of the factors. Properties of exponents. Now there was a very special exponential function. Does anyone remember the really special one? Real special. College algebra. Like, this is very general. When I write a to the x, that's very general. A can be any number as long as it's bigger than 0 and not 1. But there was one very special one.
Was that into negative a?
No. E to the x. Oh, yeah. Right? Remember this one in college algebra? E to the x. See here, a is just any number that's bigger than 0 and not 1. But if we use this number, e, which e is approximately what? 2.718, something like that. If we use that number as the base, then we call this the natural exponential function. Do y'all remember hearing about this one, e to the x? And in college algebra, they probably told you, I know I told my students, that this is a very, very special function, extremely special. And I'm actually going to talk about why it's so special today.
And then you went on a tangent.
And then I went off on something?
Yeah.
I'm sure I did. All right, so there is a general exponential function. This is a specific, very special one. Got it? Then in college algebra, after you talk about exponential functions, we then start talking about logarithms. What is special about a logarithm? How is it related to an exponential function? It's the inverse. So logarithmic functions undo exponential functions. You put the two together and they wipe each other out. But we can also graph logs, log functions, and this is what a log function looks like. This is the general notation for a log function. We'd say log base A. So that's what they look like. They have a vertical asymptote right here. As you go to the right, they grow forever. And that's what they look like as long as the base, the A, is bigger than 1. If the base is smaller than 1, then the logarithmic function looks like that. And so if we have exponential functions and log functions, and we can draw them, then there's tangent lines on them, right? And if there's tangent lines on them, then that means I need to figure out what the derivatives of these are. And that's what today is about. So this is just to get you to remember what these things look like. But there are also properties of logarithms. These properties are very important for today. Very important. More important than the properties of exponentials that I gave you just a minute ago. Do you remember a section in college algebra, which seems like so long ago, right? Where you did this thing called expanding and condensing expressions? Does that sound familiar? You take like this expression, had a bunch of logs in it, and you'd be told to turn it into a single log. Or the other way around, you had one log and you were asked to like pull it apart into a bunch of logs. Okay, to do that in college algebra, we used these properties right here. And it said that if you have a log, does not matter what the base is, if you see multiplication in the log, you can split that into 2 logs with addition between them. And does that sound familiar? If not, there they are. You'll have to go back and review if you don't have any idea what this is. Also, if you have a single log with division inside of it, you can split it into 2 logs with subtraction. And then this one, the big daddy right here, all right, this is a major, major, major formula, is that, I'm going to write it a little bit different. If you have a log, does not matter what the base is, and you have some expression raised to the n power. In other words, this right here is raised to the n. I use r here in this because that's what the book used, but I'll just use an n instead of r here. This property of logs says that you are allowed to drop the n out in front as a number and just multiply that times the log of just this thing. So no more power. The power drops out. Do you remember that property? Big time. Is that a question?
It's just like the product quotient and power rule, isn't it?
What do you mean?
Well, with the multiplication going to addition, division going to subtraction.
I don't want to say that because, I mean, the product rule, we're talking about derivatives, right? We use a product rule to take a derivative. We're not taking a derivative here, right? I haven't even talked about derivatives at all. This is just a property of logs. If you have multiplication, 2 factors inside of a single log, we are allowed to split it into 2 separate logs. And now the first factor goes into the first log, the second factor goes into the second log, and we separate them with addition. That's a no, I don't want to say it's connected at all to derivatives, because it's not. It's just a property of logs. What about this? Is there a property for this? Can I take this and split this into 2 logs or do something with it?
No.
No, you may not. There is no property for that. If you have addition inside of a log, you cannot split it up into 2 logs anyway. The only way you can split it up is if that was multiplication inside. That's it. Okay? All right. Couple of other things with logs. There was a very special log, which was the natural log, right? The natural log. So like here's some examples of logs. You could have like log base 2 of x. That's an example of a function, right? And I could graph that. That would actually look like this because the 2 is bigger than 1. I could do another one, let's say g of x is log base, let's say 1/2 of x. that one would look like this. Here's the x and y axes. Okay, that's what those would look like. This one goes like this because that's smaller than 1. But the very special log is the one where this base is e. And we do not write it like that.
No, ln.
We write it ln. You all remember seeing ln x? Okay. Why do we write it like that? You're going to miss this. This is good stuff. You're going to miss this. Do you know why you write this instead of this?
Didn't you say it was because of the typewriter?
It's because the typewriter back in the day. Because this natural log appeared so many times in publications, research papers, hundreds, thousands of times within a paper, that if you ever typed on a typewriter, you'd have to subscript. And if you do that, anyone use a typewriter ever? Yeah, I mean, so you type, right? You hit individual keys, and the little physically this thing comes up and goes, hits and stamps your paper. That's each letter is printed onto the paper, and there's no backspace at all. But when you get to subscripting like this, you had to like turn the dial, like turn the drum like a click, and then do E, and then you go back to X and then keep typing. And that's just a real pain. So we just said, look, since this comes up so much, we'll just do ln x. You could type without having to stop, and everyone just would understand that that means that. And it's actually French log natural. Right? You know the French, they do it backwards, so it's logarithm natural or something like that. I'm not French, but that's what this is. This is an ln, not an in. It's ln. With me? Okay. So we have special notation for a special log. There it is. And it looks like which of these two? Top one or bottom one? Top one, because the base is 2.718. It's bigger than 1, so it's going to look like this one. Now, the natural log is related to the natural exponential function, right? The natural log function and the natural exponential function, they're like inverses, and they have properties that we need to know. If you ever put a natural log together and you compose it with the natural exponential function, the natural log and the e kill each other off, and whatever was up here drops out. If you do it the other way around, and you take e, and in the exponent you put the natural log function, they kill each other off, and it spits out whatever was in the natural log function. So x comes out. But that only works if x is bigger than 0. Why can't x be less than 0? Log functions are not defined for 0 or negative numbers. Remember the picture of a log, right? This is a picture of logs. They look like this. You cannot take the log of a negative number. And you cannot take log of 0. It's undefined. You have an asymptote there. So this property works. They kill each other off as long as that x is bigger than 0. Other kind of subtle things we need to know. E to the 0, anything to the 0 should be what? 1, except for 0 to the 0. Right? That's different. Natural log of 1 is 0. Natural log of e is 1. This property right here you can get from the first property. That's really e to the first power. So natural log and e kill each other off, and you just get what's up here, 1. And then there's another formula in college algebra that we're not going to use this much at all. I can't think of anything we're going to do with this. But this was important in college algebra, is change of base formula. This is what allows you to do logarithms on your calculator. And your calculator only has all you need is one log key on your calculator, and you can do any log. And this is the formula that allows you to do it. We can convert any logarithm to using just our natural log key on our calculators. So, all right, that's exponential and log functions in 10 minutes. Our question today is, what is the derivative? of an exponential function, right? What's the derivative? So I thought a lot about how I wanted to approach this. And I thought I can either really try and go and do what I did like for certain rules where I proved them to you, or I could go the easier route and just kind of give you the formula. And I'm leaning to the easier route because it is pretty hard to show why the derivative of exponential functions are what they are. I mean, I could do it, it's just going to take a while and it'll eat up time, and at the end all you're going to want to know is what's the derivative of an exponential function. So I'm going to do that. For the exponential function, I'm just going to tell you what the derivative is. You're going to have to take it on faith. And then for the logarithm, I'm going to prove the logarithm to you because it's easier to prove. All right? Y'all okay with that? All right, so here we go. Let's say we have y equals a to the x. And we want to know y prime, what I mean by that is dy dx. I'm going to continue to keep this standard that we've been using. If you see me ask for y prime, I'm saying dy dx. So here's what it is. I'm just going to tell you. The derivative of that is itself times one thing. Natural log of a. Now remember, a is a number, right? A is the base of the exponential function. So if you have an exponential function, a to the x, and you take its derivative, the answer is the exponential function exactly the way it was, but you're going to scale it. You're going to multiply it by this, and this is a number. Do you agree that natural log of, let's say, 2 is a number? Natural log of 5 is a number. So all this does is changes it. It scales this function, stretches it out, does something to it, stretches it, or compresses it down. Yes?
So basically you're just multiplying by the inverse of e?
You're multiplying by the inverse. Well, it's not. It's the inverse function, but natural log, but it's evaluated at a, which is whatever this number is.
Which could be e or pi or whatever.
Yeah, let me give you a specific example of this. All right, a specific example of this would be, let's say that y equals 5 to the x. What would y prime be? Well, that first of all, you have to recognize that that's an exponential function, right? That's 5 to the x. The a here is 5. So the derivative would be what? 5 to the x times natural log of 5, which is just a number. That's just a number times this. That's it. We're done. Okay?
I think you're going to ask us more complicated.
No, I mean, it's going to get more complicated, but I mean, there's nothing more to it, all right? That's it. Now, what are some of the things I see that make me pull my hair out when I'm grading things? Well, here's something I see. I give the same problem, and the student says x times 5 to the x minus 1. So what did that student just do?
They applied the power rule.
They applied the power rule, didn't they? They brought the power out front, they subtracted 1 from the power. No. The power rule only works what? If you have x to the n, right? Then the n comes out x to the n minus 1. Notice though that when we wrote this down, x was our variable, right? N was a number. This is backwards. The variable is up in the exponent. The number is in the base. You see these are flipped. So let me give you another example next to this one. What would this be? If y is equal to x squared plus 2 to the x, what would the derivative of that be?
2x plus
2x, so derivative of each term separately, 2x plus
2 to the x
2 raised to the x times ln 2. That example illustrates the difference between the position of the variable. If the variable is in the base and the exponent's a power, you use the power rule. If the variable's in the exponent and the base is a number, then you use the exponential derivative. Yes?
You wanted us to take the second derivative, or we have to do product derivative?
Okay, good. What if we did second derivative? Let's do that since you're requesting. Let's do that. Second derivative, what's the derivative of this? Just 2? And would this be product rule is your question? Let me ask you that question and right back to you. Would it be?
Yeah, yes.
Okay, where's your product occurring?
Well, because one,
Are you seeing a product right here?
yes, because that's multiplication.
This is multiplication, but what is this? It's a constant. And constants, can't they just come along for the ride?
So you could almost rewrite it the other way.
Exactly. You could, if you want, rewrite this as natural log 2 times 2 raised to the x and just say, hey, that's a constant, it's going to come along for the ride. That's what I would do. Now, could you do product rule? Yes. But when you do derivative of this times this plus derivative of this, what's the derivative of this? 0, because it's a constant. So you could do product rule, but I wouldn't. I would just treat this as a constant. Here it is, coming along for the ride. There's the natural log 2, right? Coming along for the ride. Now I just have to ask myself, what's the derivative of 2 to the x? What is the derivative of 2 to the x? 2 to the x times natural log of 2 again. So I'm going to get 2 natural log of 2's.
So would that be
I would probably put it like this. Squared and erase that. That's what I would do.
yeah, third derivative, not up to
Yeah, let's not. You could probably see a pattern after a while. Yeah,
Either way, you won't actually ever get rid of the 2 to the x.
that's right.
that? No, you will next time.
No, the 2 to the x.
Oh.
This will never go away. You can keep taking derivatives all day long, and it's never going to go away. All right, let me try something else. Another example. Y equals 4 to the x squared plus 1. Let's do a little more. X squared plus 2x plus 1. Anyone have an idea of what I'm going to use to do this?
Yes.
What?
You do the same thing, but I think there's a chain rule.
This is going to have chain rule in it.
You're gonna
So we have to back up and kind of look at, do we have an inner function and an outer function? If I were to plug x into this, I would start up here, wouldn't I?
Yep.
I'd figure out all of that, and then I would take that and use that as the power on x, right? I mean the power on 4. So the outer layer of this is the 4 being raised to something.
Some quadratic.
And then the inside is that quadratic piece. Excuse me. So any guesses as to what this derivative would be? If the outside is 4 raised to something, what's the derivative of 4 raised to something?
4x squared plus 2x.
4 raised to that, right? Now be careful here.
Times ln of whatever's inside.
Times ln of,
X squared plus 2, 4.
careful, ln of 4, okay. Good.
Oh, yeah.
Right, it's ln of the base.
Yeah.
Times the derivative of what's up there. 2x plus 2. Correct? Incorrect. A lot of people did this on the test. I took off for it.
It's incorrect.
This is incorrect.
Why?
Well, you just did it.
Oh,
What-
okay, parentheses.
Parentheses.
Oh,
This has to be in parentheses.
yeah, okay.
It was almost universal that students were making that mistake. And it's so critical. Look, you have to think about what it means to not have parentheses. I think I showed this to you before. 4 times 5 plus 2, right? If I'm going to take the number 4 and multiply it times 5 plus 2, if I write it like that, what's the answer? 22. But if I put this in parentheses, what is it? 28, right? That's 7 times 4 instead of 4 times 5 plus 2. What we're saying in chain rule is this, right? times the derivative of what's up there. And if that turns out to be two things, it must be in parentheses. That would be it. Let me give you another one. Y is equal to x 3 to the I guess so, x cubed. Everyone see product? Right there? You'll see that product? So the derivative of a product should be the derivative of the first one times the second one plus the derivative of the second one times the first one, right?
Yes.
Okay. So what is the derivative of the first one here?
3x cubed.
Derivative of
No, the first one is just
1, right? Just 1 times this one. Okay.
So what is that?
Then what? Plus. Now the derivative of the second one. So let's kind of take our time on that one. That's like this problem, isn't it? Got like a base as a number. I've got this thing up here. So I'm going to go through the same thing. It's like a chain rule. So what's going to be there?
A to the x 3
To the x cubed. So it's itself, right? Times ln 3 times 3x squared. Perfect. Do I need this 3x squared in parentheses? I don't need it. Why don't I need it here? Because it's one term, right? This is two terms. That's why we had to have parentheses. Now, one thing that you would probably get in the book from something like this, or for a problem like this, is they would realize like that's the same thing, and they would like factor that out, and they would write 3 to the x cubed times, what would I have if I pulled it out of here and here?
3x squared times ln 3.
1, right? A 1 here, plus whatever's left here. And you could write this different ways. I'd probably write that 3x squared ln 3. The order of those don't matter. Just don't make this 9. Don't make this natural log of 9x squared. This is trapped. That can't go in there with it. Yes?
I think you forgot to multiply with the x on the second.
Oh, I forgot the x. Thank you. X here. I forgot to finish off my product rule. Here, hit me with this. Hit me hard.
It's okay. You don't like mistakes.
you get one shot.
Okay, so what I'm going to change. You're all, hey, give it to me. I'll hit you. All right. So did everyone see the x I left off the product rule?
So where's the x?
Okay. So that becomes x cubed right there, and that's what I have here.
Oh, you just did it like way ahead of time.
We are going to practice this more, but do you have the general idea of what's going on? Okay. Now, what about this one?
It's just X.
What's the derivative of this?
Oh, the derivative.
Follow the rule. So it's itself times ln of e, right? ln of e. What? But that's 1. ln of e is 1. ln of e is 1. Because remember, that's like e to the 1. I just showed you all that, right? These kill each other off. All you get is the exponent that was on the e, which is just 1. So if this is just a 1, then this is just what? E to the x.
So it's forever e to the x, no matter what.
It's forever e to the x.
I can see that on the test somewhere.
Well, in college algebra, we try and explain at that point how important this function is. And it's hard in college algebra to make a student understand just how valuable this function is. But now that you've seen this, can you tell me what makes this such a special function?
It never
The
changes.
derivative of itself,
Its derivative is itself.
which means if you have e to the x to the 99th derivative, it's just
It's always the same. There are only two functions that when you take the derivative of them, you get itself. One of them is this function. y equals 0. What is the derivative of y equals 0? 0. What's derivative, second derivative? 0. But what does that function look like? It's a flat line, right? I mean, it's just a horizontal line. It's the x-axis. And that's a pretty damn boring function. We, as human beings, at some point, were trying to answer a question. We were saying, is there a function? Does there exist a function that when you take its derivative, you get the function itself? So it is its own derivative. Does it exist? We knew this one, but that's boring, right? Who cares about that? Function's boring. We wanted to know if there was something else. And it turns out that there is one and only one other than this one. And this is the one. This is it. We don't know why it is. It just is. And it only works for e to the x. It does not work for any other base. And that's why we call it the natural exponential function, because it naturally occurs. We're not sure why. It is the way it is. That's the natural base. That's the base that creates that perfect function that we want. Now, I'm going to try and tie this into a picture. It's not perfect. You could argue what perfect means, but it's unique. It's the only one that behaves this way. There is no other function that does this. Like the golden ratio or something? Yeah. Kind of like that. It's a number that it's the only one that does what we need it to do. So do you remember that the derivative represents the slope of the tangent line, right? So like if I go back to the good old days when we were just doing derivative of like x squared, but hold off on that for a second. If I gave you right now y equals x squared, here's what it would look like. And if I said to go out to 3, you would be up here at what point? 9, right? What's the slope of the tangent line there?
2x.
Yes, that's the derivative of that is 2x. So what's the slope of the tangent line right here? 6, right? How do you get 6? You plug in x is 3 right here and you get 6. So the slope of this tangent line is 6, right? That's the slope. What we wanted to know was there a function that the slope of the tangent line was always equal to the y value of where you were? So like, look at the e function. E to the x. What is its derivative? Itself. Okay, so let's go out to, let's say, 2. Where are we on here? E squared, right? That's where we are. That's how high we are. But guess what the slope of the tangent line is there? E squared. The slope of this line is equivalent to the height of the point off the x-axis. Yeah? That's the only function that behaves that way. You will never find a function that does that, where all you have to do to know the slope of the tangent line is to know the height of the point. There is a direct connection between how high you are and that slope. All right, so it's a very, very important function. So let's take some derivatives with it. How about this? Y equals e to the x times sine x. What's the derivative of this? What do you see here?
I see a product.
See product? Good. There's a product right here. So you're going to do derivative of the first one times the second plus derivative of the second one times the first one. So what's the derivative of the first one? E to the x. And you do not need to write down natural log of e, because that's always going to be 1. So you just write down e to the x. Times sine x. Okay, next. Plus cosine x times e to the x. And the book would most likely not leave it like that. They would probably factor out the e to the x and put sine x plus cosine x here, like that. Yeah, do it. Just get used to it because you're going to have to do it. We're getting really close to that point, very close, where I said that we're going to have to start setting these derivatives equal to 0. It's coming. I can see it. It's around the bend. And we just need to get used to this sort of manipulation. All right. How about this one? What's derivative of that? It's kind of like that one I did with the 4. Was it 4 raised to the x squared something? Same story. So it's chain rule, right? So what do I have? E to the x squared minus 4x times natural log of e, which is 1,
Times 2x minus 4.
times 2x minus 4. Oh, okay. All right, just making sure.
I'm skipping parentheses on everything just because.
Yeah, you have to be careful with that. Some people will just start throwing parentheses on everything. They're like, okay, then I'll put like a parentheses there and like a parentheses there and parentheses there and then parentheses there. And they think like the more parentheses they put, like the safer they are. You have to be real careful with that sort of thing. Because you can actually put too many parentheses and you can create bigger problems.
Well, that's technically not even correct.
That is correct still, by the way.
We are just in parentheses.
All right. Whoa.
Just watch on the next episode. Just have that everywhere.
Can we just have e to the x on our test the whole way?
You just want me to give you 20 problems of e to the x?
Yeah.
Okay. Okay. Y equals the square root of x plus e to the 3x. Do you remember back when we were doing derivatives with limits? And I gave you the rule, the first rule, power rule, and y'all were like all excited. I said, but the functions will become more complicated, right? I mean, this is an example of a complicated function. This is not a function you would study in college algebra, right? Or in pre-cal. It's very complicated, but it has a graph. And we're trying to figure out the derivative, which would give us the ability to talk about its instantaneous rate of change at any point in time, or at any x value. See chain rule? What do you see as the outer thing? Square root? Square root of junk. Okay, so the derivative of this should be 1 over 2 square root of everything that was in there, right? That's the outer function, the square root. That's the derivative of a square root of some junk. Times the derivative of what's in here. Now that's 2 terms, right? So I can do them individually, but that means I'm going to need a parenthesis because I'm going to have 2 answers, right? May as well throw that parenthesis in right now. Give myself space for both terms. What is the derivative of this first one? 1. Okay, great. Plus the derivative of e to the 3x.
E to the 3x.
E to the 3x itself, right? Times
Parentheses 3.
the derivative of what was up there, right? Because there's a little mini chain rule in this, isn't there? You take derivative e to the 3x as itself, but then you take derivative of what's up here, and that's 3. You don't need parentheses here.
Yeah, but just in case.
Yeah, this would not be wrong. That would not be wrong. You understand the 3? Okay, so let me just go back. We just did, what was it, e to the x squared minus 4x? We did that one? So when we took the derivative, it was itself, but then we said times the derivative of what's up here, right? Which gave us the 2x minus 4. Exactly the same thing. The derivative of e to the 3x is itself, but then times the derivative of what's up here, the derivative of 3x is 3. So that's going to pop out right there. We all good with that? Now we could leave it like that, but I'm willing to bet the back of the book would have this. Two. All they did is they said, look, you see this big thing right here? It's like up in a numerator, they just slid it on top of this.
Why did the y prime equals a to the x times the natural log of a?
What's that, what?
I'm
Oh, the
still
natural
stuck
log of e part?
Yeah, I'm still stuck on the 3 part. Like, I don't understand that.
Are you,
Because
are you,
because if you're taking the derivative of e to the 3x,
Mhm.
isn't that
itself
times natural log
of e, which is always 1.
Okay.
So we never really have to include that.
Okay.
If you wanted to, there's a natural log of e right there. But then times the derivative of what's up here, which is this 3. I guess what you can do is anytime you're taking derivative of e to anything, the natural log part will not be in there. But if you're taking derivative like 5 to this something, then you have to put that natural log 5 in there. Just going to take some practice. All right. Let's move on. You'll have plenty of time to practice. I did the homework. I have not posted the solutions yet. I have all the videos done. I had to do 3 different videos because I was busy. I'll post them all on YouTube tonight after class. This next section, this section we're in right now, 3.3, there are a lot of homework problems. It took me a while. It's like 1 through 15, then 17, 18, 20, 22, 24, 25, 28, 35. There's at least like 20 or 30 problems. But it's all derivatives. That's all it is. Derivative, derivative, derivative. All right, we're done with exponentials. What's the derivative of a logarithm, of a logarithmic function? So this one I'm going to prove. All right, let's say that we have y is equal to log base a of x. And I would like to know what the derivative is, right? I want to know what is y prime. So here's what I'm going to do.
You're going to take the natural log.
I'm going to do this.
Does it have to be a 5?
Oh, wait, why did I put 5? Sorry. Sorry. That's my fault. My fault. I don't know why I thought that was a 5. It should be a. Thank you. A. What I'm doing is I'm using something that we talk about in college algebra about the exponential and log functions, both of them being one-to-one functions, which means that it was this in college algebra. It said this: if a to the x equals a to the y, if and only if x equals y. So if x is equal to y, that means you can rewrite this as a to the x equals a to the y. So if you have an equation, you have equality, you are allowed to write this. And that's what I just did. Now, why did I do that? What happens on the right side? If I put the exponential function a raised to something, and in there I put log base a, how are these two related to each other? They're inverses, right? And so these will kill each other off, and all you'll be left with on this side is what? X. So you have a to the y equals x. So what I did, that first couple of steps there is just algebra. Now what I'm going to do is take the derivative of that implicitly with respect to x. Remember implicit differentiation? Yes.
That was a to log a to the x inverse.
These, right? A to the x and log base a to the x, those two functions are inverses of each other. Which means that if I take this expression and I put it right there, which is this, it'll spit that x out. If I take this right here and replace it right here, they'll kill each other off and it'll spit the x out. Because they're inverses. Remember, the property of inverses is that if you take a function, you compose it with its inverse, then it spits out x. And it goes both ways. So if you want, you can go back and you can review those sections a little bit if you want, if you're like uncomfortable with the idea of the inverse. But yeah. All right, so implicit differentiation with respect to x. Implicit respect to x. So when we do implicit, we have to take derivative of each side. What is the derivative of a to the y with respect to x? This is tricky. What's derivative of a to the y with respect to x? Well, what's the derivative of a to anything?
A to the y. A to the y.
A to the y.
Times.
Hold on. Are you looking it up? You got it? You got it? You're not looking it up? I thought that's what you were doing. Okay. All right, so I guess we'll have to do it without the help of the Wolfram Alpha or Google. What's derivative of a to the y?
Itself. So
Itself, right? Because a to the y is an exponential function, right? Y is dependent on a variable somehow, right? Y depends on x, so derivative of a to the y is itself times the natural log of a. One more piece.
the chain also.
Chain rule. The derivative of what's up here, which is dy dx, which I'm going to call y prime. Is that okay with you? That's the derivative of the left side.
Parentheses.
No parentheses. I'm done on the left side. Right side equals, what's the derivative of x? With respect to x? 1. What am I solving for? Y prime. Can you isolate y prime for me?
Yeah, you just divide everything.
Yeah, you just divide everything. So how about this? 1 over a to the y natural log a. So I just took this whole big chunk, divided it out, and that's what I get, right? And I'm happy. Not yet. I'm almost happy. There's one more thing I want to do.
You can't have natural log in the bottom right.
No, natural log's okay on the bottom. This is just a number. 1 divided by a number, that's just a number. Who cares? This is a problem, though, because I'd like my answer to have x in it, not y. But if we come back over here, what is a to the y?
X.
It's x. So this is just 1 over x natural log a. That's the derivative.
That's cool.
It's kind of like when you're taking the second derivative, you get the first derivative, put it back in there.
Yeah, okay, yeah, sure. You're replacing something with something you had earlier, yes. I thought you were going to say that's kind of like product rule. I was going to, no, I don't want to say that. Okay, so look, this is just proving to you what the formula is, all right? That I proved to you, but end of the day, what do you need to know? You need to know that the derivative, if y is equal to log base a of x, you need to know that the derivative of this is 1 over whatever's in here times natural log a. That's it. The way I look at it, when you take the derivative of a natural log, it like drops what it has in there, it just drops it down to the bottom. And then the log goes away. You have natural log of a down here. That's your formula. Shall we practice with it? Sure, okay. So let's try this as an example. If y is equal to log base 7 of x, what's y prime?
So 1 over x natural log 7.
That's it. That seems straightforward? Okay. Let me tweak it just a little bit. Turn the screws just a little bit. Y is equal to log base, or how about I don't write base? How about I just write log, and then inside I put x squared plus x plus 1. Uh-oh.
That's not a problem because it's assumed that that's log base 10.
That is log base 10. Okay, so if you write log without a number down here, it's assumed that that's a 10. So you need to know that, because when you come to do that part with the natural log of a over here, you need to know that that's a 10. So the derivative of this is a chain rule, everyone. This is a chain rule. The outside function is log. What is the derivative of log of something? 1 over, and then it's just going to like spit out this, right? It's going to spit it down here. X squared plus x plus 1 times ln 10. Ah, good. Now that's the correct use of parentheses right there. Because that natural log of 10 has to multiply times whatever this is, and if that's more than one term, then it's got to distribute.
Then you can have another parenthesis outside.
Then I've got more to do, right? Because all this is the derivative of log of something. I still need to follow up with the derivative of what's in here. Chain rule. So out here, in parentheses, I have 2x plus 1. Which you would probably see written this way. Like that.
Probably like break these two to be 2x plus 1 because that's where you do that. Or not.
Yeah, I don't know what they would do. I would think that they would probably leave it like this. Questions?
How do you want that on a test?
I want to see parentheses, man. That's what I want to see. If I'm going to be honest, I want to see this with the correct parentheses.
Just start putting parentheses in there. It's like,
Right. All right. All right, well, you'll have to practice with that, because imagine, I could throw an x in front of this, right? And then you would have like a product rule, but inside that you'd have a chain rule. So,
Then you have another chain.
yeah. But let's do this one. What is the derivative of the natural log of x? What is the base of the natural log? What's its base? Like log log, it was base 10. But what's the base of the natural log? E. It's e, right? So what is the derivative of log of something? 1 over that something, right? Times natural log of the base, but this base is e. What's natural log of e? 1. So this is just 1 over x. That's the clean one. The derivative of natural log of x is 1 over x. Beautiful.
that's actually kind of cool.
Yeah. So if we extend this out a little bit more and try something a little harder, how about natural log of Are they putting trig functions in there? Let me see if they throw any trig functions in here. Yeah, they did some. All right, let me try that. Cosine, let's do that. This is actually pretty cool, this one.
Oh, it's negative 1.
What is the derivative of the natural log of something? The natural log of something. What is the derivative? 1 over, that's something. Okay, so it's 1 over whatever's in there. You don't have to come in here with a natural log a, because it's just going to be a 1, isn't it? Times, I heard it, that's correct. The derivative of what's in here. Negative sine x. And I could slide that on top, and that's negative sine x over cosine x, which is just negative tangent x. How could I have got the answer to be tangent x instead of negative tangent x?
That would have to be a,
What would I have had to do?
oh, no.
I'm just wondering, like, if you can tell me what that would have had to have been to make this tangent, not negative tangent.
Oh, you could have had the negative inside the argument, a negative cosine x.
I could have done a negative in here. No? Why not? No, because that would be 1 over negative cosine, right? And then you would have positive. Yeah, how about a negative in front? Just negative on the front. Wouldn't that just, it would come along for the ride? Do y'all see that? So I want to show you something. If I did this, I'll put it as a -1 too, because I'm about to show you some cool shit right here. Okay, so watch. So what if I, sorry. What if I do that? Does everyone agree that that's going to give me tangent? Yes? I'm not going to take derivative though. I want to show you something. Are those the same? Whoa, what just happened? What just happened? What just happened? What did I do? What? Yeah, look at this right here. You see the -1? Remember I said that really important property of logs? Really, really important property? I even showed it to you like this. I said if you have something raised to the n, right, and that thing's being raised to the n, you can drop that power out, and it can become n log base a of that something, right? Well, the property works both ways. If I have something out here, I can push it up as a power. So what I did is I took this -1 and I pushed it up as a power up here. And when I put this to the -1, what does cosine to the -1 mean? 1 over cosine. And what is 1 over cosine? Secant. Right? So if I were to take the derivative of this, what should I get? What should I get? You remember what I said I wanted? I wanted just tangent, and you said, oh, just throw a negative out in front. And I said, fine, yes, I agree, that will work. And then I did something weird, and I did this. The derivative of that better be tangent. Do you want to try it? Try to take derivative. What's the derivative of natural log of anything? Or natural log of something? 1 over that something. Okay, great. Times what's the derivative of secant x? Secant x tangent x. See it? Tangent x. It's almost scary sometimes how this works, how all this stuff. It's like math is this perfect puzzle that no matter how hard you may try, you can't screw up how perfect it is. Like I mean, if you say, like that little -1 there, I mean, everything I did was right, and then this still worked out exactly the way it should have. I mean, it's impossible. I mean, you can screw math up, obviously, but it's impossible to find like an example where the algebra doesn't match up or work. Like it always works. It's crazy. All right, 215. Y is equal to sine x ln x. What do you see? Product? There's your product. Derivative of this should be cosine x times ln x plus derivative of natural log of x is 1 over x times sine x. Parentheses. Right, there we go. I just put parentheses around everything.
You might want to do that on the cosine x too.
Yeah, I better not leave that one out. Okay, there we go. There. And that's it.
So
Well,
yeah,
you could slide
no,
the sine
the
x
sine
over
x
x.
over x isn't that like 1 or something like that from way back in the day?
What, sine x over x?
Well, you could slide
If we were taking a limit, if we were taking